So here's that starter question again. Now I'm going to use this as an example of how we can create a model that really helps us understand this properly, because we saw that it's actually quite paradoxical in and of itself. So let's see if we can understand it. Now we've got two things constantly going on. We've got information about ill people here. So the number of healthy people becoming ill each day is 1%, and we know about ill people becoming healthy, which is 19%. So let's try and start thinking, well, how are we going to represent this? Well, every day this updates, which is perfect for a recurrence relation. So we're going to have two things in our recurrence relation, something that measures ill people and the number of healthy people each day. So this is ill people each day. And this is healthy people each day. Let's apply that then. So, and this is where my little starter, the number of ill people tomorrow is going to be, so the starter is going to help us see where this comes from. The ill people tomorrow, will 19% of the ill people get better, but 81% are still ill. So that's going to be 0.81 times the number of ill people yesterday. So the number of ill people today will be 81% of the number of ill people yesterday. Plus, we've got the 1% who become ill who were healthy. So 0.01 times HN. Now that's a really nice relationship, but it includes INs and HNs here, which is not helpful. So let's see if we can eliminate one of those. Well, we can. And we can eliminate one of those because we know that the number of healthy people plus the number of ill people is always the whole population. There's no other possible category that you can fall into in this particular scenario. So the whole population is either ill or healthy, so that must equal 5 million. And so HN is going to be 5 million take away IN. Well, let's plug that in. Now, you'll see this is similar to what we did a little while in the second set of examples in task 1. We're going to plug this bit here in instead of our HN. So we end up with IN plus 1 equals 0.81 IN plus 0.01 lots of, and instead of HN, we're putting this in. So we've got 5 million take away IN. Now we're on to something because that's all INs, so we can simplify. So IN plus 1 equals, we've got 0.1 IN, 0.81 IN, take away 0.1 IN, because we've got a minus and a 0.1 there. So that leaves us with 0.8 IN. 0.1 times 5 million is 50,000. Now we're on to something because we can look at this and we can go, hang on, this is a recurrence relation. The number in front of IN is less than 1, so it converges. Well, we can find the limit of a convergent recurrence relation because we did that last week. So let's put in our limit is equal to 0.8 times our limit. Don't want times that. Plus 50,000. Let's take 0.8L off each side, so we get 0.2L equals 50,000. Divide both sides by 0.2, and we get L equals 250,000, which is the limit that I promised you in the previous video. So, looks like a super complicated question, but really there's 3 key steps. The first one is being able to take information out of the question and turn it into a recurrence relation in terms of 2 factors instead of just 1. The second is to identify the link that gives us the whole population and use that to replace one of our 2 factors in the original recurrence relation. Once we've got that, rearrange a little bit and find the limit of that recurrence relation. And this gives us a really good sense of what's going on with this situation. We can tell in the long run what number we're likely to balance out at. Now for something a little bit more lighthearted for the your turn, because I want you to see two examples of this. So in Bees Like School here, the number of pupils is 700, and they're all, you can assume this, they're all either using an iPhone or an Android phone. Okay, so we're not worried about any other types of phone. We're not assuming there's people that don't have a phone. Here we're going to assume all 700 have a phone and they either use an iPhone or an Android. Now every year 10% of the Android users try to be trendy and become iPhone users. The rest stay on Android. But due to the price of iPhones, 14% of the iPhone users choose to swap to Android. And I want to know in the long run what percentage is going to end up using each operating system. So pause, have a go, and I'm going to run through this one in just a moment. Great, so hopefully you paused. Hopefully you've had a go. Let's try and start getting our information out. So we've got information here about iPhone users, and we've got information here about Android users. So those are going to be our two categories. So we're going to have our AN people, which are Android users on a given day. We're going to have our IN. So these are iPhone users. Each year, sorry, I shouldn't have said each day. Each year. And these are Android users. Each year. Now, it doesn't matter which one of these two you track. At the moment, I'm going to follow Android users, but if you've done it for iPhone users, it will all still work out. You can still figure out the same answer. So the number of Android users, well, 10% of the Android users switch. That means the number of Android users is only 90% or 0.9 of the Android users we had last year that have stayed on Android. But 14% of the iPhone users changed to Android. So 0.14 times the iPhone users have changed to Android too. So here's our 90% that stay with Android. Here's our 14% that switch from iPhone to Android in the following year. Now we want to also have this connection written down, which is the Android users plus the iPhone users in a given year is 700 because it's all the pupils. That means the iPhone users are 700, take away the Android users. Plug that in, so we end up with AN plus 1 equals 0.9 AN plus 0.14 lots of 700 take away AN. Now we've got a bit of rearranging to do, but we're well on our way to an answer here. So let's do that little bit of rearranging and figure that out. So we get AN plus 1 equals 0.76 AN. And now we need to do 0.14 times 700, which I believe gives us 98. That's given as our recurrence relation. Now we want the limit. So the limit equals 0.76 L plus 98. Sorry, I should have said converges as 0.76 is less than 1. That's kind of an important detail. We're taking 0.76L off both sides. So that's 1L, take away 0.76L. So that's 0.24L. And that equals 98. Divide both sides by 0.24 and we get 408.33. Now, in this case, it's particularly important. We're talking about users of iPhones or Androids, so it makes sense to state our answer in a much clearer way. So in the long run, we expect 408 Android users and the rest, so 700 take away 408, which is 292 iPhone users. And we're finished. So another situation completely different from our first one, but the same type of maths can let us analyze what happens over time with these two groups. And anytime you've got a situation where you've got two groups changing between one thing and another, you can analyze it in this sort of way and get yourself a long-term trend of exactly what's happening. So have a go at the questions, and then there's one more video for this week, which actually extends a wee bit beyond the content of the course, but hopefully it's quite interesting and shows you another use of recurrence relations in the real world and a relation to the real world. And then really your key main other task for this week is to get started on the revision process. And so we've put up some past papers for you to have a go at.